Okay, and we can prove that these are extraneous just by plugging in the numbers. The negative square root of 11. You know what? I did not copy those down right. Oh my goodness. Let me erase this here. So the root, I have 1 plus square root of 11. So what I really need to have here, oh my goodness, I can't believe what I did, is I need to have this as 0 equals x plus 1 plus the square root of 11 and x plus 1 minus the square root of 11. And that's because if you multiply these out, 1 times 1 is 1. 1 times negative square root of 11 is negative square root of 11. But then you have a positive square root. Those two would cancel each other out. But then you would have a positive square root of 11 times the negative square root of 11, which would give you negative 11. 1 minus 11 is negative 10. So anyways, there's our two factors. According to the zero product property here, the first one would state that x will equal negative 1, because you would add subtract the 1 across, minus the square root of 11. Notice that's extraneous because that's a negative number, and the log, this natural logarithm must be positive. Over here, you would have negative 1 plus the square root of 11, and square root of 11 is larger than 1, so that would be a positive number. So that one would work. Okay, so there was, I told you we could check out this by graphing, and so that's what I'm going to do now. Is I'm going to show you here. Let's just graph these equations, and I'm going to graph each function and show you graph. So the first one is the natural log of x plus 10, the first one being function f, minus the natural log of x, and then f2, which will be our g of x, which we'll get a natural log, whoops. Let's try this again, natural log of x plus 3. And if you notice, oh no, our function g is a logarithmic growth, function f is decay. We have one intersection, menu, analyze graph. That intersection is at that point right there. And we could check that out. Let me go ahead and capture that here. And what I'm going to do now is I'm going to add a page, go to a calculator, and type that in. Negative 1 plus the square root of 11 is what we thought our answer, our solution should be. It's 2.3166. So when we look at our point here, we drag this in. Notice that's the same point, 2.32. That's the same x value we're getting right there. So I'm going to go ahead and write that in, that this is approximately here. If I rounded it, that was 2.316, I believe. Let me check that. 2.317. I'm sorry, 2.317. 2.317. That was approximately the value, which is what we see right there. The intersection of the two graphs. So you can go through the DOL. Obviously, you use a calculator technique like I did there, or you could do the algebra as I did above. Okay, so now let's finish up this packet. As we look, we have an equation 5, or excuse me, example 5 and example 6. Let's take a look at these now. Example 5 says find the inverse of the following function. So a reminder, as when you go to find your inverse, the first thing you do is you switch your x and y. So this is y here. What I would do is I would say this is x equals 3 times 2 to the power of y plus 4 minus 15. And now to completely find the inverse after switching x and y, what you do is you isolate the new y. So I'm going to add 15 to both sides. And this negative 15 does not combine with the 3 because that 3 is multiplying. So I have x plus 15 equals 3 times 2 raised to the power of y plus 4. Now what I'll do is I'm going to, that 3 is multiplying, as I mentioned a second ago. So what I'm going to do is divide by 3. That's the inverse operation, the opposite here. And you could distribute these if you want and say this is x over 3 plus 5. If you like, you could write it that way, or you can leave it in this form, whichever form you want. That's equal to 2 to the power of y plus 4. Okay, so now what happened is I've isolated this into a exponential function. So the way to solve an exponential function is you convert it to a logarithm. So what I'm going to do here is I'm going to take it this way and say this is the same thing as log with a base of 2, but instead of raising it to the y plus 4, I'm going to raise it over here to the x over 3 plus 5. And that's equal to y plus 4, which brings me to my final step here. My final step to isolate this logarithm, or excuse me, I get y by itself, is to subtract 4. Now, this subtraction of 4 will be outside the logarithm because this subtraction of 4 is outside of the logarithm. So now that I have y by itself, I'm going to use the traditional f negative 1 to symbolize that this is an inverse function. That's because exponentials and logarithms are both functions, would equal log base 2 of x over 3 plus 5 minus 4. That would be our inverse function right there. And if you wanted to note the domain here, this has to be positive. So you could solve your domain by stating that x over 3 plus 5 must be greater than 0. And you could solve that quickly. You would subtract 5. You would subtract 5, and then you would multiply by 3. So I subtract 5, multiply by 3, and I'm getting negative 15 there. Let me do this way. Minus 5, and then I would multiply that by 3. And so x has got to be greater than negative 15. That would be your domain as well. Now let's take a look at slide some of this over, and then we'll look at the next problem here. Well, I'm not sure if it'll let me slide all this over. There we go. Let me slide that over. Okay, so now let's look at G, and we'll do the same inverse operation. So first, I need to change this to a y, and so I have x equals negative 3 log base 5 of y minus 4 plus 6. Now, if I wanted to try to isolate this logarithm, the first thing I need to do is get rid of this plus 6. So I'll subtract 6 from both sides. And so we have x minus 6 equals negative 3 log 5 of y minus 4. And now negative 3 is multiplying the logarithm, so I'll divide by negative 3. Once again, I'll go ahead and distribute this division. So I have, these are going to become positive. The minus 6 will become a positive 2. But I'll have minus x over 3 like that. So negative 6 divided by negative 3 became a positive 2. I wrote that in the front. That equals log base 5 of y minus 4. Okay, now that the logarithm is isolated, I'll convert it to exponential. And so I could say 5 raised to the power of 2 minus x over 3 equals what the logarithm originally looked like it was raised to, y minus 4. And so the last step here, to isolate that y, because we would add 4 to both sides. And finally, we'd have our inverse. So this is G, I'm sorry. This would be G inverse would be 5 raised to the power of 2 minus x over 3. That's just so hard to see. Let me write this over here. So G negative 1 of x would be 5 raised to the power of 2 minus x over 3 plus 4. 3 is just so hard to see. That would be my inverse. And for exponentials, the domain is all reals. Because of a logarithm, its range is all reals. So here, the domain would be all reals. So I'll go ahead and just put that in right there. And that would be my solution. On part G. So now that you've seen me do this twice, one thing I could point out, notice that this was a horizontal shift right 4. Over here, you have a vertical shift up 4. Notice this became 4 on the x-axis, so you shifted right 4. This became up 4 on the y-axis. Over here, this was a vertical stretch and a vertical reflection. We have inside a negative x, which means a horizontal reflection. And instead of multiplying our y values by 3 here, it looks like dividing by 3, which, because x is a liar, would actually mean to multiply by 3. So yeah, instead of multiplying y's by 3, we multiply by x by 3. Notice the transformations are exactly opposite. Same over here, same concept. If you're wondering, why is this looks like a minus 15, this would be a minus 5. Well, you'd have to multiply by 3. So again, it'd become a minus 15. Here you go, as you would see there. Okay, so that's how transformations work. Here's a DOL for you. For what values of x does k of x equal 1? And I want you to think of k being the inverse. So this is saying k of x equals 1. That's saying the y value equals 1. For what values does the y value equal 1? Think on that. And it'll help you out on solving that. All right, our final example, example 6. Find the solution to each inequality. Remember to restrict the domain of each logarithm. So what we're going to do here is we want to know, for given the function f, what values of x is f greater than 0? So what I'm going to do here is substitute. I want to know f of x is greater than 0. So I'm going to take this function and say, where is log of x squared minus 4x plus 7 minus the log of x minus 3 greater than 0. And there's 2 ways you can do this. One is I could add this logarithm across and then do one-to-one property, which is probably the easiest way of doing this. Or I could do quotient property, make this into one logarithm as a fraction, and then convert to exponential. I prefer, honestly, what I'm gonna do is add this logarithm across and do one-to-one property. I think there's fewer. I think it's more likely that I don't make an error if I do it this way. So what this will do is this will make us have log of x squared minus 4x plus 7 is greater than log of x plus 3. And now I can do one-to-one property. I'm going to do the one-to-one property here. That's what I'm doing, 1-to-1 property. And so that will tell us that x squared minus 4x plus 7 has to be greater than x plus 3. And what I'm going to do now is set this back equal to 0. I'm going to subtract an x from both sides. Subtract an x, and I will subtract 3 from both sides. And so I want to know, where is x squared minus 5x plus 4 greater than 0? And so I'm going to x method this to factor. So what I'm going to try to do is factor this, and I'll use the x method as it's a trinomial. So I'm factors of a times c that add up to b. Here I have a, b, c. So it's 1 times 4 is 4. Add it to be -5. So the factors of 4 are 1 and 4 and 2 and 2. To get a combo of 5, it has to be 1 and 4. To make it -5, they both need to be negative. So I could rewrite this as, to get x squared, it'd be x times x. To get a -5x plus 4, it would be x minus 1 and x minus 4. All that greater than 0. Now that right here, we could say that either, and so if these were equal to 0, we would have a 0 is at +1 and at +4. So what we do now is I'm going to create a number line. And what we're going to test are the values to find out where is this greater than 0. We're going to test those zeros there. So that would be at 1. Let's put that at 1, and then 2, 3, 4. We're going to test those values. And you also need to test, you need to be aware of any values here. X has got to be greater than -3. And over here, this logarithm, if we factored off that, let's see here. 0, -1, -2, -3. The graph cannot be -3 or this way. It's got to be something over here. And so these are the values we're going to test are from -3. I know it's got to be greater than. And here, let me just real quickly, if I plug in a -2, that becomes a 4 -8. Okay, we're good. Let me just plug in -3. -3 is 9. -3 times -4 becomes a +12. That's a positive number 2. We're going to be good in there. Even if, yeah, we're good. So I'm going to plug in numbers and determine if these are positives or negatives in here. So using these values, and I'm only going to plug in values between -1 and -3 and 1, between 1 and 4, and then numbers greater than 4. So I'm going to pick a number between -3 and 1. How about we plug in 0? Let's see what we get if we plug in a 0 here. I want to know if this will be greater than 0, or I could do it over here. If I just plug in a 0, what I'm looking at is, let's do f of 0 now. F of 0. What I have is log that 0 squared is 0 minus 4 times 0. I guess for your sake, I'll plug it in one time so you get to see it all, see what I'm doing. Plus 7 minus log of 0 plus 3, which means I'm looking at log of 7 minus log of 3. That right there is greater than 0. That is positive. How do I know? Well, because this is log of 7 over 3. No, I'm sorry. This would be log of 7 over 3. Yep, that's quotient property. And we want to know if that's greater than 0. That's saying 10 to what power is 7/3. And that's going to be, yeah, that'll be a positive number. Why am I off here in my brain? Log of 7, let me just show you. Log of 7 minus log of 3. That's positive because log that's a growth function. So it's growing, so 7 should be greater than 3. Yeah. And I could also do log of 7/3 here. And see that it is positive. So it's greater than 0. So we're good there. Now, because this is a positive number, I'm going to just put a plus here. This area here, this part of the inequality, we're going to have a positive set of answers. Anything between -3 and 1, those critical points. So now I'm going to try one between 1 and 4. How about we try the number 2? So I'm now going to try the number 2 because that's between 1 and 4. So if I tried f of 2, what I'm looking at is log of 2 squared minus 4 times 2 plus 7. I'm getting all this, I'm plugging in right up here. Minus log of 2 plus 3. Okay, what happens this time? Well, we would have log of, this is 4 minus 8. That's -4 plus 7 is 3. Log 3 minus log 5. That's going to be less than 0. Again, you could rewrite this as log of 3 over 5. And that is, let me change colors here. This is going to be less than 0 because again, this is growth. That's log base 10. That's growth. So 3 is going to be underneath log 5. That is less than 0. So in here, in this range, we have negative values. So that's not going to be part of our answer. Now we're going to pick up a number bigger than 4. How about we pick the number 5? So any number bigger than 4, I'm just going to select a 5 and let's test that value. So if I plug in a 5, let's see what we get here. F of 5 would be log 5 squared minus 4 times 5 plus 7 minus log of 5 plus 3. And when we go to simplify, that's 25 minus 20. That's 5 plus 7 is log 12. It's log 12 minus log 8. That will be greater than 0. Now, how do I know that? Because those are growth. And I could rewrite this as log of 12 over 8. Since that's greater than 1, 10 to the 0 is 1. Since that's greater than 1, this is greater than 0. And so this is positive logarithms over here. So here's what we just found out. Our values for which f of x is greater than 0 are going to be the intervals. Our intervals between -3 and 0. So we cannot be equal to -3. And we can't be equal to any of them since they're inequalities. So it's going to be anything in between these two intervals here. So from -3 to 1, union, and then from 4 to infinity would be my other answer choices. So now let's graph this and make sure that our graph agrees. So let me open up my graph here. I'll go new document. Graph. We have the log. And this is the easy way of doing this problem here from the get-go. Minus 4x plus 7 minus the log of x plus 3. If I graph this, I want to know what intervals is this greater than 0. You can see it comes from -3 up until 1. That's at 1 is equal to 0. That was where that value was there. And then 4, 2, 3, 4, from 4 on to infinity, it's greater than 0. And that's what we got. So our answer is in fact correct. And I could slide this over so you could tell. Let's take a picture of this. Where is it? That's not where I want to go. And I'll throw in the picture here so you can look at that later. So very complex problem there. Why did I choose the -3? If you're wondering, well, when I looked at the logarithms, I knew x had to be greater than -3, so that was the earliest possible answer we could have, that we could not have a value left of -3. I got that from that one logarithm. That line right there is x equals -3. So the answers had to be greater than that. And we found these two zeros right here after doing the zero product property. That's where we got those 3 values from, the critical point. And then we just tested to see if the math was positive or negative there. So because that was a lot, let's try another one. What if we want to know where g of x was less than h of x given these two functions? So the algebra here, I'm going to substitute in the natural log of x squared plus x minus 5. And I want to know where this is less than the natural log of x plus 4. We could, again, here's what I know right now as far as my answers go. According to this natural log, x has got to be larger than -4. Let's see, let's say this is 0, -1, -2, -3. Here's -4. We must be on this side of -4. And we want to know where g of x is less than h of x. We could try to do a little x method here. This is going to create some values here. Be 1/2, 1/2. I'm dividing that by 2. There's not going to be good factors, -5 that add to 1. So I'll have plus the square root minus the square root. Let's see, to get -5, 1/2 is 1/4. So that's 1/2 times 1/2 minus some value. It's got to equal -5. It's gonna be 5.25 or 5.25. Let's see, that would be divided by 21 over 4, I believe. The square root of 21 over 4. 21 over 4, which is a really weird number. That's going to be those values. X has got to be these when you plug them in. Well, I'm going to do the math here and then we'll simplify that later. Let's do one-to-one property. We should really just look at the graphs to figure out the answer here first, just make sure we do it right. But x squared plus x minus 5 is going to be less than x plus 4. I'm going to combine my like terms. Subtract x and subtract 4. Subtract x and subtract 4. This is going to give us a real nice equation here that x squared. These go away as well. It's going to be minus 9. It's less than 0. That is the difference of squares. You could factor that if you wanted to by x method. Factor is -9 and add to 0. You're going to find out it's going to be x plus 3 and x minus 3 is less than 0. Okay, so coming over here, the number line. The values I know I need to add would be -3. We need to test -3 as a break and +3. 3 at +3, we also need to test any values in there. So we need to test something between -4 and -3. And let me real quick plug that in. Well, -3 even 9 minus, yeah, we're good there. Okay, we'll test numbers in between -3 and 0. And then again, we'll test values between 0 and 3 and then larger than 3. So we got a lot to plug in this time. We could use the calculator. Let me actually use calculator first. Make sure we don't make any mistakes here. So the first function we're going to look at is going to be the natural log of x squared plus x minus 5. And there's those two values I was telling you about from right there. And then our second equation is the natural log of x plus 4. We want to know when our g of x, our first function, is below our second function, is less than below. So when is the blue below? So it's going to be below in here up until that amount, and then over here where it picks back up. So I'm going to, let me go menu, analyze graphs. I'm going to do an intersection here so you can see this point. Yeah, analyze, do another intersection so you can see the point. Here we go. Screen capture page. Okay, so what I'm seeing, I'm going to explain this to you as I go. This graph has 3 asymptotes. I'm going to try to color coordinate here. The first asymptote is here at -4. So this goes with the red, which they call it F2. Our F2 was our H equation, which is H. So this has the asymptote x equals -4. Well, the blue has 2 asymptotes as well. I don't want this to stand out too much. Let me make this thinner. Okay, now I'm going to copy this. And the blue has 2 asymptotes. So it has one here. And it has another one right here. Now, if you're wondering, what are those values that create that asymptote? And this is the equation G here. This is x equals, it's going to be -1/2 plus the square root of 21/4, which is the same thing as the square root of 21/2. And this one right here is x equals -1/2 minus the square root of 21/2. I just took the square root of 4 there, is all I did. That's where these two asymptotes are, and I can do that math for you over here so you can see it. Control dot new page, calculator, -1/2 plus the square root of 21/2, and the same thing again, but this time it's minus. Those are the two x values that these asymptotes appear on. That's approaching here. You can see it's coming right down. And I think the calculator actually has a tool doing this quadratic formula. Let's see here if I remember where it is. Menu, algebra, polynomial tools maybe? Yeah, find roots. There we go. Degree 2. Yeah, we have a degree 2. We want the real roots. We have an a of 1, a b of 1, and a c of -5. And let's see, hit enter, and notice these are the same two values that we just got right there. So those are the values. I didn't make a mistake on that. Those are our asymptotes. Notice that when we would test it, these are the values we'd have to include on there as well. So now that we know what those are as roughly a decimal, let me come over here, and so I don't have to go back and forth. Let me just take a picture of it and add it in. Make the longest problem longer. What we have here are these two values that I'm going to add in. This right here would be -2.79, would need to be in here somewhere. -2.79. And then you would also need to add in 1.79. 1.79. And so honestly, we would need to test in between -4 and -3. We would need to test between -3 and -2.79. We need to test between -2.79 and 0. We need to test between, no, we don't need to test between 0. I added that. Anywhere between -2.79 and 1.79. No, actually this graph, the blue would not exist in there. So we don't have to check this part. The blue graph would not exist in between those values. So we need to test in between these two values here. Here, there, and there. Those would be the 4 windows. And as it turns out, if you test anywhere over here, your blue equation, which is G, is greater than, or the H doesn't even exist. So we don't have to test this one either. So because H doesn't exist, okay, we don't have to test it. We need to test between -4 and -3. In between, here's -4 and -3. Notice the G is above the H. So this would not be right. This on this one and here, that interval G is greater than H. So that would not be part of the solution set. But in between here, we have a solution. Between these two spots, we have a good solution. So I'm going to do an open circle, and that would be shaded in there. There, we don't have a graph on the blue, so we wouldn't look at that. But we'd pick back up over here. That's the wrong symbol. Let me do an open circle. Oh, I see what happened. Let me just do a little eraser so I can. There we go. And the green needs to be for the second line right there. Okay. So in between 1.79, which is here, the red is up above. And so that's where we wanted the second answer. We want the red up above. And so all this would be good up until that point at 3. So those are our two windows. We're looking at only answers from -3 to -2.79. or if I wanted to add a zero, or I mean a decimal, I'd put 1 on there. Union, and then once again in between this window, which is 1.791 to 3, which is a pretty crazy little answer there. But that's where that's where it would actually work. That was some wild math. I'm not gonna lie, that was some wild math in there. That's how you would find these critical points though. So critical points we found there at x equals -3 and +3. We would get them from up here whenever you plug those in, and from right here. These are all critical points. The asymptotes, everything else. So let me add this asymptote here. That's a -4, sorry, -4. And then these over here, which is 1/2 plus and minus the square root of 21/2. That's a lot of critical points you'd be testing between, but that's where it'd work. Whereas on the previous one, we didn't have nearly as many critical points. Critical points we found here were at 1 and 4. Critical points where x equals 1, 4, and I've forgotten the asymptotes. That was -3, it looks like. Yeah, -3 right there. And this does not have any real roots. I don't know if I talked about that, but I could tell it's shifted up for only being shifted left 2 units, excuse me, right 2 units. It's only going right 2 units. It's shifted, it hits the y-axis at 7. That wouldn't do that. It would go down to 3, I believe. The vertex would be right 2 up 3. So that would never hit the x-axis. So we don't have any critical points to test there. It was only these values, -3, 1, and 4 that we really need to test. I wrote down the ones I did test, 0, 2, and 5. But those are the values, how you do that. So there's a lot there. You can try this one. What I would just recommend is you plug the stuff in. You can use the calculator, and if not, you can work through your algebra. This will be a little easier because it's not a logarithm, but that's how you do these type of problems.